basic jargon related to error analysis, and now some rules on quantities that are being measured in very many ways, right? So there could be a quantity that could be the sum of two measured quantities A and B. A and B are two quantities, they are measured differently. And now there is, in quantity A, delta A, let's say, represents the absolute measurement error in measurement of A. Delta A is the absolute error in measurement of A. And delta B is the absolute error in measurement of B, where A and B are measured independently. They are out of different experiments, right? And now we have to deal with a quantity X, which would be A plus minus B. X, which is A plus minus B, where A is a measured quantity obtained out of one experiment, B is a measured quantity obtained out of another experiment, and we have knowledge of delta A and delta B. Delta A represents the absolute error in measurement of A, delta B represents the absolute measurement error in measurement of quantity B. Now if we have to deal with X, right, which is sum or difference of A and B, then the absolute error in measurement of X, is given by plus minus delta A plus B. Even if this is minus, this will still be plus. Absolute error in measurement of X would be error in measurement of A plus error in measurement of B with a plus minus on either side, right? And obviously the fractional error in measurement of X is going to be delta X by X. So that's as far as X being sum or difference of two quantities measured in different ways through different experiments. Then the absolute error in measurement of X would be error in measurement of A plus error in measurement of B. Even if this is minus sign, the absolute errors in measurement of A and B will only add up, right? Now, then there is a product rule. If again A is a quantity measured one way and delta A is the absolute error in measurement of A, B is another quantity measured in some other experiment, and delta B is the absolute error in measurement of B. Now if I want to find the fractional error in X, given that I have knowledge of absolute error in A and if I have knowledge of absolute error in B, then the fractional error in X, this is fractional error in X. X is not measured, only A and B are measured. This is the fractional error in X, right, is going to be plus minus fractional error in A plus fractional error in B. Fractional error in A plus fractional error in B. That's going to be the fractional error in X. X is not measured. A and B are measured, but X is computed. So if X is computed and we have knowledge of fractional errors of A and B, then the fractional error in X could be sum of the fractional errors in A and B, right? Then X could be a product of this kind. A to the power m into B to the power n. Once again, if delta A represents the fractional error in A, the absolute error in measurement of A, and delta B is the absolute error in measurement of B, then the fractional error in X, given that X is going to be this, is going to be m times fractional error in A plus n times fractional error in B. That's going to be the fractional error in X, right, in a product. And whatever holds good for a product also holds good for a ratio. That means if I have X is A power m by B power n, then the fractional error in X is going to be m times fractional error in B, A, fractional error in A, delta A by A, plus n times fractional error in B. Even though this will appear in the denominator, the rule for the product and the ratio will remain the same, in the sense it's not that this will become a minus sign, this will still remain plus. So fractional error in X then produced is going to be m times fractional error in A plus n times fractional error in B. So we must take notice of all of this. This gives us, if we have a certain number of quantities and we are trying to measure errors in a computation involving those quantities, then these rules will come in tremendously handy. Thank you so much. Bye bye.